Okay, we're going to move on to problem number 9, my problem number 9. And it has a block sliding down a ramp and then colliding with a second block. So let's go ahead and read this. So a small block of mass m, that's this one, is released from rest at the top of a curved frictionless, that's key, it's frictionless ramp shown above. The block slides down the ramp and is moving at a speed of 3.5 VO. I don't like the fact they use V0 because I like to use that as my symbol for initial velocity, so that means I have to use something else for initial velocity because they use that for just the general velocity of the block. So it collides with the larger block of mass 1.5 m, that's this one, at rest, so it's not moving initially, at the bottom of the incline. The larger block moves to the right with a speed of 2 VO. Again, that's just their general designation for this velocity. So there it is, 2 VO. Immediately after the collision, express your answers to the following questions in terms of the given quantities and fundamental constraints. Okay, whatever that means. So in other words, they're not going to give you real numbers to work with, or not too many of them. Okay, so what's the height? What is this height here? So here's a principle that you should understand. And we've talked about this. If this block has a mass m and it's not moving, then all of its energy is potential energy. So that P equals mgh, formula we've used a lot in this class. Okay, so the height times gravitational acceleration of 10 times its mass. Now we said that if that block falls straight to the ground, initially it has no kinetic energy because it's not moving. And all the energy is potential energy. If it falls to the ground, just before it hits the ground, all of this energy turns into kinetic energy. And none of it is potential energy. Why? Well, because just before it hits the ground, it has no height to it. If it has no height, then this whole term goes to zero. It has no potential energy. So all of this turns into this as it falls down. Now here's a different question. What about this block? It's starting at a height h, but it's not falling straight down. It's sliding down this frictionless ramp. And let's just say before it hits this block. I'm going to just draw a dashed line to represent this block right here, just before it hits. What is its kinetic energy? We know that if it fell straight down, we said its kinetic energy would be the same as the potential energy up there. But what about this block? What will its kinetic energy be? And the answer is the same thing. If it's frictionless, it doesn't lose any energy sliding down the ramp. That's what frictionless means. So it has all of the energy that it had as potential energy up here, it has down here. All the ramp did was change its direction, but it still has the same amount of kinetic energy that's equal to the amount of the potential energy up here. Same as this block, except this block's falling straight down, this block is curving down a ramp. Okay? So, therefore, if we can know the kinetic energy at this point, we will know the potential energy up here, and since we know mass is capital M and g is gravitational acceleration, we know those numbers, we can figure out the height. So let's figure out for part A, make some space here. So A, we're going to figure out height equals question mark. That's the way you abbreviate that. Height equals question mark. So let's figure out the kinetic energy. Okay, so that's the instantaneous velocity when it gets there. So that is going to equal 1/2 times its actual mass. And again, instead of giving us a number, they just call it capital M, but that's meant to be a definite number, a definite value. And they said that its velocity is 3.5 VO. So 3.5 VO is its velocity when it gets down there, and you square that. Okay? So I'm going to just give you the clue in on how they gave this answer. They don't ever square the 3.5. They don't actually, that comes out to be something like 12.25. They don't ever do that. In fact, the way they deal with the numbers is kind of funny. So here's what you do. you go ahead and write this as m. Let me actually put the 3.5 in front. They square the 3.5. They square the 3.5 and the VO separately. Okay. And what do we say that's going to equal? That's the kinetic energy, but it's also the potential energy up here. It didn't lose any energy. So that means this is going to equal mgh. And I should have written this m for the mgh, I should have written it as the capital M. That's the M. Okay? So now this is the kinetic energy here, which is equal to the potential energy up here. So now we have a way to solve for H. So let's just do some algebra. I'm going to rewrite this as M. Then they square the 3.5 and they square the VO squared. That's just the way they presented it. It wouldn't be wrong if you actually did 3.5 times 3.5. They didn't do it that way, so I'm just going to do it the way they did it. There's nothing wrong with doing it the other way. Just going ahead and doing all the numbers. Okay, now we're going to divide both sides by M and G. Okay, so M and G on this side. Okay, again, anything you do to one side, you do to the other, so M and G cancel and cancel. And this is what you have over here equals the height. That's what we're looking for. Now we can still do one more cancellation. And you know what? I forgot my 1/2. So there's 1 over 2. I'm not going to write the 1 on top. I don't need to. I'm just going to put the 2 down in the bottom. It's 1/2 there. Okay, now the M's cancel. And so what I end up with, H equals 3.5 squared VO squared over 2G. And that's the way they present the answer in AP Classroom. And that's that. Okay, so that gives you the height. Okay? All right. Now they want to know the speed of the small block after the collision. So here comes block of mass M. It comes down here. It hits 1.5 m, and that goes 2. So this is just a simple conservation of momentum problem. Okay, so I'm going to draw a line here. I'm going to write before, and what we have is when it gets here, it tells us that the velocity is 3.5 VO. So we have m, which is capital M, that's the mass, times the velocity when it gets there is 3.5 VO, plus the momentum of this one before. These are all before. All of this right here is before. Well, let's not write that. What is it? If it's not moving, it says it's at rest. It says this block down here is at rest. Larger block to the, it says it somewhere. 1.5 mass is at rest. That means this is 0. Okay, so that means the total velocity here is m3 is 3.5. Let me just write it better. Is 3.5 VO times m. That's the total momentum before. Now after, what is it? Well, it's got to equal 3.5 VOM, and after it is m times its unknown velocity after. So I'll just call that VA for V after, or VAF for V after. And I'm going to circle that because it can get confusing with all these V's. That's what we're looking for. That's what we're trying to solve for. Plus this mass, 1.5 times 2 VO. That's mass times velocity. So 1.5 m times 2 VO. Okay. Now I'm going to bring all of this down here because I'm running out of space. And in fact, I'm going to use a second piece of paper coming up here pretty soon because there's just not enough space for all this. So here we go. The velocity, let me write that neater. It is just not neat. It's 3.5 mVo. So that's what the total momentum over here has to equal. Momentum before, momentum after. So let's write that as an equation down here. So I'm bringing all of this down to here. Equals m times the velocity we're looking for at block 1 after, so I'm going to circle that, plus, now let's just simplify this. 1.5 times 2 is 3, so I'm going to call that 3 mVo. Okay. Now we're solving for this, so I'm going to subtract this from both sides. This goes away, and this becomes 3.5 minus 3 is 0.5 VO. Okay. Excuse me, MVO. I forgot that M right there. It's 3.5 minus 3 is 0.5 MVO. That equals this. Equals MVF, what we're looking for. So I am going to divide both sides by m. It cancels on this side. It also cancels on this side. So over here, I'm going to write my final answer for part B, is that the final velocity of the little block, that's what it was asking for, speed of the small block, equals 0.5 VO. And that's the answer. The final of the little block equals 0.5 V0. Okay? All right. Now we go on to C, and I'm going to do that on a separate piece of paper. You're welcome to do that. You just be sure anytime you do anything on a separate, you label it very clearly. And label it very clearly, use my number, the handwritten number, not the problem number. Okay? Otherwise, I won't know what you're doing. All right, here we go. The larger block slides a distance d. So let's write down what we know. We're talking about the larger block. So we know the mass of the larger block equals 1.5 m. The distance that it moves is capital D. That represents an actual fixed number, but they don't give us that number. They just are going to call it D. All right. What else do we know when that block slides? It says D before coming to rest. So that means we know its final velocity is going to be 0. Okay. And its initial velocity, and I'm going to have to call that V initial or INI initial. I'll just write it out. Initial. Why? Because they used VO for their variable here, so I can't use VO for initial velocity. But they tell you what it is. It's this number right here. If you can see that, let me move it up a little there. It's 2VO. That's what they said in the problem. Okay, so that's 2VO. All right. So, okay, so how do we do this? Well, we have a formula. There's only one force acting on this block. Let me move it up here. There's only one force acting on this block once it gets hit by the little block and starts moving this way. The only force acting on it is a friction force. So if we drew that as a very simple sort of free body diagram, 1.5 m, its only force, its velocity, this is not a force vector, its velocity is 2VO this way, but the force, the only force acting on it is the friction force slowing it down. That right there. Okay. So what is the value of that friction force? Well, the formula for force that we know is mass times acceleration. Now remember what we're looking for, and I should write this down. It's mu equals question mark. We're trying to find mu. What mu is, it's question mark. So friction force is not what we're actually trying to get right now. So let's figure out what the friction force is. It's the only force acting on it. Well, we know that the mass is 1.5 m. But what's the A? What is that? How can we get it using this information? So one of the reasons I want you to get used to writing variables out like this is because then the formula sometimes jumps out at you. Not always, but sometimes it jumps out at you. In this case, the formula we want to use is one of the 5 kinematic formulas, which is this. VF squared equals, now be careful here, the formula uses V0. It's not that V0. That's a very specific number. This is the generalized initial velocity. So V0 squared. That's why I hate them using that here. It's just bad. But the rest of the formula is minus 2 acceleration times change in position times change in position. Let's just call it delta x. That's the formula that's on your formula sheet, your orange colored sheet and on your green sheet. Okay, so let's plug in numbers. Final velocity is 0 equals the initial velocity squared. So what is that? It's this VO, 2VO squared minus 2 times acceleration. And what's the delta x? It's the distance. That's the change in position. It's a straight line, so it's distance and change in position is the same. D. Again, why are we doing this? We're trying to find A so we can plug it into F equals ma and figure out what the friction force is, the only force acting on the block. Okay, so let's go ahead and solve. So you square this first. 2 squared is 4. Don't forget, you have to square everything in there. VO squared minus 2AD. Now I'm going to add 2AD to both sides. Okay, and this one goes away. And so what you have is 2AD equals 4 VO squared. We're going to divide both sides by 2D. This D cancels, this 2 cancels, the only thing you have left is A, so that's going to be the acceleration. 4 VO squared over 2D. Okay, all right. Now let's go back to this and plug in. Or let's just go ahead and do it right here. We're going to bring this on up to here. And we're going to say times 4 VO squared over 2. And I used small d. I should have used capital D. That's a very specific distance that block traveled, like that. Okay, now I'm going to have to bring it down here anyway because I need some room to work. So friction force equals, I'm just going to copy it again, 1.5 m times 4 VO. All right. Okay, so now we simplify. So I'm going to do a little math. I'm sure you'll follow me. 4 divided by 2 is 2. 2 times 1.5 is 3. So this, and this are taken care of. So that becomes 3. Okay. 4 divided by 2 is 2. So this all becomes a 2. And times 1.5 is 3. 2 times 1.5 is 3. Okay, then I have m VO squared over D. What is that? That's the friction force. Now we have a formula that says this. Friction force equals mu times the normal force. What is the normal force on a flat surface? There's the block, there's the normal force, there's the weight, mg. Okay. So we're going to multiply. So what we're going to do is solve for mu so that we have friction force, that's the number we just have found right there, over normal force equals mu. All I did was divide both sides by Fn. Okay, so I hope that didn't trick you. Okay, there it is. So let's go ahead and write that over here. It's 3 mVO squared over D. And now what's the normal force? It's the mass, which is 1.5 m times gravitational acceleration. You don't have to call it 10, just 1.5. Okay? Now simplify the numbers that you do have. 3 divided by 1.5 is 2 up on the top. mvo squared over dg. Oops, I forgot to do something. I forgot to cancel this m and this m. These m's cancel. I missed that. So that means this m's no longer there. Then there's no m on the bottom either. So it's 3, excuse me. So it's 3 divided by 1.5 is 2. The m's canceled out. V0 squared over dg. And that is the final answer. So let me write it more cleanly down here. Boy, I'm really at the bottom of a page here. Mu equals 2VO squared over dg. And that is the final answer for the coefficient of friction. Right there. Okay, D, it says indicate whether the collision between the two blocks is elastic or inelastic. It's if the energy is conserved, if the KE total before is equal to the KE total after, then it is elastic. If it's anything other than equal, it's inelastic. Okay, so let's figure out what that's going to be. Let's go back to our problem up here. So the KE of the small block, so this is the small block before, and large block before, so let's figure those out. So KE equals, for small, is going to be 1/2 capital M, and just before they hit, it's 3.5 VO squared. Okay, the KE for the larger block, again, it's not moving, so you don't even have to do the calculation. The velocity is 0, so the kinetic energy is 0. Again, if something is not moving, it has no kinetic energy. So let's just simplify the numbers in here. So it's simply going to be 3.5 squared, that's the way they like to write this rather than actually calculating it, VO squared times M over 2. Okay, so that's what the kinetic energy on the other side has to equal. So let's see if it does. So the so this is small. Well, I'm going to do it down here so I have some space. This is the small block after. And what was its velocity? We figured that out here. It was 0.5 VO after they collided. So after is going to be 1/2 M, and then it's 0.5 VO squared. That's the small block. Large block after. Okay, and that's going to be 1/2 times the mass, which is 1.5 M, times the velocity after, which they said was 2 VO squared. Okay? Alright, so this one, 0.5 and half is 0.5, so that's 0.25. Again, 1/2 times 0.5, which is also 1/2, is 0.25. I'm writing it in decimal. M VO squared. Plus 1/2 times, well, let's just, 2 squared is 4. 4 times 1/2 is 2. And 2 times 1.5 is 3. Follow me on that again. Do the math however you want to. It's just arithmetic. 2 squared is 4. Then that 4 times 1/2, 4 times 1/2 is 2. Half of 4 is 2. And 2 times 1.5, you can do it in any order of multiplication, is 3. Okay? Then we also have an M and a VO squared. So the VO squared, MVO squareds, okay, are common, so you can add this. So 3 plus 0.25 is 3.25 MVO squared. And 3.5 squared is 12.25. You can do that on your calculator. Divided by 2 is 6.125, something like that. So I'm just going to write it out. Okay, you do it on your calculator if you don't believe it. 6.125. I just did this squared and divided by 2. And that's M, and then the VO squared. So this does not equal this. That's an equal sign, does not equal. So it's inelastic. Okay, and that is the end of problem 9. It's a very difficult problem. I will have you do it several times before this course is over. At least one more time to practice this, because if you can get good at a problem like this, all the other problems will seem easier. You take a difficult problem and you do it over and over again until it becomes very second nature, and then all the other problems seem easier. All right.